Hello, Physics 2B Section 7. This is going to be the last video I record specifically for you guys. There's another video that you'll have available for lecture for next week, but you guys don't have class on Tuesday, so I've done a pre-recorded lecture of everything that I cover in that lecture on Monday for the other sections. Okay. You're watching the lecture video here right now. You've got a discussion. The discussion is a review of different ways that we think about light. So a lot of the stuff we covered today and a lot of the distinctions from reflections, refractions, and diffraction for the last week and a half. All right. There will also be a discussion for next week, which you might want to do over the weekend. And that's basically a practice exam. Okay? So you have basically a practice exam for that discussion. There's a practice final available here. There's nuclear notes that go along with the last lecture. And then if you're in section 7, some of the other sections watch this video as well, then that's when you have your final. And then you're done for the semester. That's a little bit of a ways away. Do let me know beforehand if you're going to have any trouble with that time period. I would like to know a couple days beforehand, if at all possible. That way I can reschedule things as need be so that there's no surprises and there's fewer sources of anxiety, because finals week has already too many sources of anxiety. So communicate and make it one less thing. All right. Today's lecture is going to start off with a big review. Then I'm going to be interjecting some important stuff about atomic structure and how that plugs into what we've been talking about with light. Okay. So, we've talked about the speed of light. The speed of light in a vacuum being a very specific value of 3 times 10 to the 8 meters per second. But that's the speed of light in a vacuum. If you have light going through a different medium, it'll have a lower speed due to its index of refraction. And here we have some common indices of refraction. We talked about what transparent meant, kind of like how glass in the visible spectrum is transparent, but glass in the infrared spectrum is not. So what you think of as being transparent depends on what type of light you are considering for that substance. I go back and forth a lot between wavelength and frequency, and energy a lot today as well. So if you are looking for the wavelength, you can say it's the speed of light divided by the frequency. Or if you're looking for the frequency and you're given the wavelength, just the opposite. The energy of light is Planck's constant multiplied by the frequency, and I'll be using that later as well. But make sure you know the distinction between wavelength, frequency, and period. A lot of people get wavelength and period messed up. They both measure a wave, except for one is measuring the length of a wave, and the other is measuring the time for a wave. So length for the wavelength, period for the time period. While that interaction is happening, where light's traveling through a different medium, it's going to not only have a different speed, but it's also can have a different wavelength. The period is constant, the frequency is constant, the energy is constant, but the speed, the wavelength, and the direction change. For the direction, we spent a long time on the derivation for Snell's law, using these Huygens surfaces, these circles coming out of points, showing the ripples of light coming forward, which eventually led us to Snell's law. Reflection, on the other hand, was much easier. Angle in equals angle out. Straightforward. The main thing, make sure you're always measuring relative to normal of the surface. If you have light starting inside of a medium, sometimes it can't get out. Specifically when it's approaching the surface at a large angle, the critical angle, or larger. So you can have both happening at the same time. You can have both a reflection and a refraction occurring. Which leads to many applications. Rainbows, fiber optics, mirages, prisms, more prisms, and then I opened up other ways that light can bend. Other ways that light can bend led us to lenses. When we got to lenses, we defined converging and diverging lenses. We looked at ray diagrams to think of, okay, what's the path that the light takes, and where do the images form? Then we got to calculating where that position was, and also figuring out the magnification of these images via height and via distances. We did multi-lens problems, and then we came to mirrors. Mirrors were very similar, same equations, but very different drawings, and therefore different conventions as well. Next, interference patterns. Interference patterns are all about electric fields overlapping. Okay? They could overlap to become constructive, they could overlap to become destructive. There could be path length differences that cause different waves to be either in sync or out of sync, resulting in constructive or destructive. If it's constructive, we get our bright spots. If it's destructive, we get dark spots. And when we went for the double slit interference pattern, we were able to look at this and say, oh, where exactly do the bright spots occur? And we found that this equation works very well as long as we have a small angle, which is to say the y value is significantly smaller than the length. If you are at a large angle, it's best to use sine of theta for each bright spot is equal to m lambda over d. Single slits, it ended up with the same equations except for a w for the width of the slit, and all the results were backwards. Okay, so bright spots were dark spots, bright spots were dark spots, and dark spots were bright spots. Went into y, extrapolated to diffraction gratings. Diffraction gratings are excellent. They're really good at getting you to separate light in a very predictable way, and for a lot of precision measurements that are used in laboratory settings, diffraction gratings are the go-to choice for spreading out the spectrum of light. Not too many emails yet. Mostly it's students saying, hey, can I turn this in late? So, looking for clarifications? Do come to me. I skipped this video and instead talked more about the nature of light. Light acts like a wave, light acts like a particle, but light is this quantum mechanical stuff. I kind of glossed over the particle stuff here, but I will be going in more detail about particle stuff at the end of today's lecture. Keeping it going. Another interference topic. Note the key is to have a path length difference, and for this one we have the thin film interference patterns, which tell you just how thick a film is, depending on what angle you are looking at it from. And again, really good precision measurements, and if you have a detector that's not your eyes, you can tune these things to get very, very specific and absurdly accurate interference patterns. Much, much smaller than a nanometer with the high precision stuff. Any cool stuff after this? I will talk a little bit about lasers today, just not on this slide. Fabry-Pro cavities, skipping those. We got wavelengths lined up, skipping that one. How do I see a laser? Skipping that one. Light emission. Now we're talking. Okay. Why do we see light? Well, we see light because it's coming towards us and it's received by our receptors. When that happens, the light hits our eye and it causes a charge to accelerate. Same thing happens the other way. If a charge is accelerating, it can send out light. Okay. So the key is for light to be formed or received, a charge needs to be accelerated. How does that work in an atom? Well, in an atom, we've got our nucleus at the center. That nucleus will have protons in it. And it'll have neutrons in there as well. And in the one I drew, 8 protons, 8 neutrons, we're looking at oxygen 16. Okay. And around that, it will also have some electrons. There should be 8 of them for this thing to be neutral. So I'm just going to keep it cartoony. So we got a pair of electrons going around like that, a pair of electrons going around like so, a pair of electrons going around like so, and a pair of electrons going around like so. Okay. Now this is a complete cartoon of the motion, but since we've studied some circular motion, that's the one that just makes a little more sense. It's not actually what happens though. And I'm not going to get into the actual shape of the orbitals. There's a lot of interesting shapes that these orbitals can be in. It's not just circles. And more so than that, it's actually a cloud of probabilities, because there's some additional quantum mechanical stuff where the actual location of the individual electrons is probabilistic. It's not at a specific point. It could be at a smear of locations, especially when it's going very quickly. So let's move away from this cartoon drawing and do a different cartoon drawing. These electrons can be in different orbitals, and those different orbitals have different energies. So there's a central area, and there's a orbital around that, orbital around that, orbital around that, orbital around that, and each of these orbitals can have some electrons in them. Okay. And again, this is still cartoony. This is not, they're not actually going around in circles. Okay, so nucleus there. What I want to point out is that the ones close in are trapped in a valley of potential, a very low potential. The ones that are further away are closer to being free of the atom. So we have our low energy atoms, n equals 1, orbitals. We have an n equals 2 orbital, n equals 3 orbital, n equals 4 orbital, and it goes on from there. An important thing of note about these orbitals is they are countable. And when I say countable, that's another way of saying quantized. Okay. So quantized, quanta, it's all about something being countable. This is where the term quantum mechanics comes from. Or quantum physics or quantum chemistry. It's that we have countable energy levels, distinct energy levels, so that if an electron was going to try to be there, it couldn't. It can't be between energy levels. It has to be at the energy level. Now this drawing is rather cumbersome. Instead, I prefer drawing these energy levels as a ladder. So we have our very low energy level, our n equals 1 energy level, n equals 2, n equals 3, n equals 4, and there could be a whole bunch of them all clustered together, and then there's some free. So that's, if an electron gets up there, it's free of the atom. But below that dotted line, it is still bound to the atom. All right. So we can have electrons here. And I'm just going to put 2 per level. Now I'm going to pretend. I'm going to pretend that I know specific energies for these different energy levels. And I'm going to just make up specific values. Instead of units of joules, though, I'm going to use units of electron volts. Okay? Because we're looking at a difference in electric potential, where a charge of an electron is going through a different potential provided by the nucleus. Okay. We have 0 EV at free, and I'm not going to do all those little lines in the middle, so I'm going to do a -1 EV, -3 EV, -6 EV, and -13 EV. What does this have to do with light? I thought this whole thing was supposed to be about what light is emitted. Well, if an electron jumps from one level to another, more specifically falls from one level to another, it's going to lose energy. And that lost energy is sent off to the environment. So that from my 4 to 3 drop is a drop of 2 EV. If for my drop from n equals 3 to n equals 2, that's 3 eV, 6 eV. That is a 3 eV drop. Next, from 6 to 13, that is a 7 eV drop. And then there's other drops that are possible. What if it dropped 2 levels at a time? Such as from 4 to 2. The 4 to 2, that'd be a drop of from negative 1 eV to negative 6 eV. That'd be a 5 eV bit of light. And we have just a few more drops we can do. A drop from 3 to 1. That'd be a drop from negative 3 eV to negative 13 eV. So that'd be negative 10 eV. Except the energy of the light itself will be positive. And lastly, we have our big drop from 4 down to 1. From 4 down to 1, that would be a 12 volt electron volt drop. Okay. So what type of light or what energy of light can this theoretical atom either send out or receive? It can send out a 2 eV, 3 eV, 5 eV, 7 eV, 10 eV, or 12 eV light, where that's a measure of the energy of the light. It's a pretty quick conversion from that to joules. Okay, if you want to convert EV to joules, all you need to do is multiply it by 1.6 times 10 to the negative 19. And that'll convert your electron volts to joules. All right. And for reference, that's the charge of an electron is where that number came from. A big distinction I want to make clear. We have a negative 1 electron volt energy level. But that doesn't mean that we can have a 1 electron volt drop. We have a negative 6 electron volt energy level. But we do not have a 6 electron volt light that comes out of there. Because the light isn't from what the energy is, it's from what the energy difference is. Okay. Let's take a look at what this means for an actual atom instead of this silly atom that I made up. So instead of my silly atom, hydrogen's an excellent option. Physicists love doing stuff with hydrogen first and getting all of our ideas for how to do stuff, and then when it gets more complicated, we say, oh, that's chemistry then. But at least I tend to do that. So hydrogen. What are we doing with hydrogen? Hydrogen has a bunch of energy levels. There's more than 6 different energy levels. And the jumps down to those energy levels each have different numbers. So if the electron drops to the first energy level, that's the Lyman series. Balmer's dropping down to the second. Passion, or Bohr series, dropping down to 3. Brackett 4. Fund 5. Humphreys 6. And there's others that just don't have special names. We're going to focus on the Balmer series. And the reason why we're focusing on the Balmer series is because there is that's the only part of the hydrogen spectrum that we can see. That's as you can see highlighted here. visible spectrum. Okay, we've got some much smaller wavelengths here, so that would be like ultraviolet light. We've got infrared light here, microwave light here. So we've got a whole range of different wavelengths of light that can be emitted or absorbed by hydrogen. But we're going to focus on the ones that we can see. Balmer series. Here we see the visualization similar to what I did earlier of having the circular orbitals drawn. Big note about this, energy levels are not to scale. It would require a logarithmic scale that you just don't want to see. So this is cartoony, is the way I like to say that. For the Balmer series, we have wavelengths of 656 nanometers, 486, 434, and 410 nanometers. Those are in the visible spectrum. That 410, that's a purplish light, like a deep purple. The 434, that's a dark blue. The 486, that's a very teal looking color, maybe aqua. And the 656, that's red. That's the color that you get from each of those transitions, from 3 to 2, 4 to 2, 5 to 2, 6 to 2. There are other transitions that occur as well, but we don't consider them. Because for the Balmer series, we can see that red over here, we can see the teal over here, we can see our blue, and we can see our violet. Okay. There's also a 397 nanometer light for the jump from 7 to 2. We can't see that. Okay. Maybe in the dimmest of environments you might be able to see it, but if it's emitting that color, it's also emitting all the others. So this specific, so our vision basically cuts out at 400 nanometers as the smallest wavelength that we're able to see. So there's some exceptions where some people have a slightly more of a range, slightly less of a range, but the cutoff that I see more often than not is 400 nanometers. On the other side, the cutoff is close to 700 nanometers. So that's our range of what wavelengths we're able to see. Where did these numbers come from? These numbers came from the Rydberg formula. With an atomic number of 1, Z goes away. The Rydberg constant, this is for hydrogen specifically, so we have this value here for the Rydberg constant. I've never used that many digits. Usually 3 or 4 is more than enough. The N1, that's going to be the lower energy level. So for the Balmer series, N1 is 2. Don't forget to square it to make it 4. And for your N2, that's going to be your 3, 4, 5, 6, 7, etc. And then you can calculate the wavelength. And you can, once you've calculated that wavelength, don't forget the inverse at the end, because much like the capacitor and resistor and all, the distance to the image equations, people still forget the inverse at the end. What does this mean what does this mean? This means that if you make hydrogen glow, you put a voltage across it and really get those atoms going, it will glow. Uh, it'll be purpley. This teal is not very bright, and red. The red's going to be really bright. So what you get is this kind of purpley lamp, and you can shine that light through a prism. You can shine that light through diffraction grating, and it will spread it out into this spectrum the way we see it. You can also have an absorption spectrum. So if you've got a really bright light source and you shine that light through hydrogen, it will block just these colors. Because the hydrogen can't absorb the other colors, it can only absorb these four and the others in the much bigger spectrum. But as far as the visible spectrum goes, it's just those four for hydrogen. What's special about hydrogen is physicists and astronomers have a very long history with observing hydrogen, because they found out that the stuff that stars are made of is hydrogen. Because when they looked at stars, they sent that light through a prism, or they bounced that light off of a diffraction grating, and then had that go to a plate, so that each of those stars, it wasn't just a spot of light anymore, it showed a spectrum of light. And each of these stars had a red line. Had a teal line. Had a blue line. And had that purple line, at least for the visible spectrum. In addition, I missed one. In addition, there were other lines in there as well that would just fill in, and because there wasn't just hydrogen there. Okay, there could be sodium, there could be helium, there could be carbon, nitrogen, oxygen. So, and the more chemically diverse ones will have a whole bunch of lines in them. But you can still pick out that specific red, that specific teal, that specific blue, that specific violet. So that thumbprint, that's easily identifiable spectrum was in every single star. And what that told astronomers a little over 100 years ago, it's about 120 years ago, is that each of these stars is largely hydrogen, and there's clouds of hydrogen around them as well. Okay. So that is the hydrogen spectrum. Okay. You can also get light from lasers using special considerations of what's going on with different energy levels for different materials. And if you find a material that has a setup where there's a fast transition and a slow transition, and you are able to pump in a bunch of energy that will take electrons from down here to up here, the fast transition will then make it so that those electrons actually more so congregate here. So there's always like one there and a couple there. But when you have something like this where there's more electrons at the higher level and fewer electrons at the lower level, That's a population inversion. Okay. And with that population inversion, you get a steady light flow of a very specific frequency or wavelength or color out of the laser. Okay, so I've got a green laser pointer. That one I think is actually using diodes, so that's a crystal mechanic that they use. But helium neon lasers, they use these lasing transitions in order to send out a very specific wavelength of light. So the helium neon lasers have a 632.8 nanometer wavelength. That's specific to a transition that you can have with the helium neon mixture. Okay. So far we've got one very specific light, color of light coming out, and that's called monochromatic. Mono for one, chromatic for color. One color coming out of that's a monochromatic source. Here we've got polychromatic sources. Okay. More specifically, it's a discrete polychromatic source. What that means by discrete, that means that there's space where you're not getting light between the different colors. That the light is separated. That's what it means by discrete here. Okay. So atoms, molecules, they're really good at sending out discrete polychromatic sources. And if you finagle with them, you can make it so they just send out one color instead. We can also have a continuous spectrum of light. How do we get a continuous spectrum of light? Well, any continuous spectrum is definitely going to be polychromatic. And you get this by having random collisions. What does that mean? That means that you heat something up. Could be a gas, it could be a piece of metal, it could be a lot of things, but you heat it up. Let's say some gas. And because of the nature of it being heated up, it has some temperature. And at that temperature, each atom will have some sort of average kinetic energy and some average speed. But it's actually not just the average. There's a whole slew of different speeds because some atoms are slower, some atoms are faster when you have a big mix of gas. Okay, so you've got a whole bunch of different atoms all moving with similar but slightly different speeds, and they're randomly colliding. Now, they could collide perfectly and not emit any energy. That'd be your elastic collisions. They could hit and combine. That'd be your inelastic collision. Or they could just deflect off of each other. And if they deflect off of each other, they're going to lose some energy. So each of these random collisions is going to end up in a loss of energy. Remember that about collisions. Momentum's conserved for all collisions. Energy is not. Energy is only conserved if the collision is elastic. So, what colors can this emit? Well, if I graph this out, let me see, wavelengths versus how bright the light is. So the intensity. 0 wavelength, nothing. Infinity, nothing. In the middle, you get a hump. It's basically the same shape no matter the temperature. A little skinnier for some temperatures. Let's make this for fire, for example. Fire mostly emits red. And it also emits in the orange and the yellow. And where's my orange? And it also emits a lot in the infrared. But when you get to the greens and stuff, not really. Barely any. So it doesn't really emit much throughout the entire spectrum. It's mostly just in the colors that we see, the reds and the oranges, and the infrared, which we feel as heat. That's a fire. What if we have something hotter? What if we have something hotter like a star? Okay, so our star has a black body curve. In that black body curve, it's got red light and it's got orange light that's being emitted, and it's got yellow light that's being emitted, and it's got green that's being emitted. In fact, that's the peak color that's emitted. Blue, indigo, violet, etc. And also a fair amount of ultraviolet and a fair amount of infrared. But it peaks at the green. That's our sun. So it's sending out. It's also sending out microwaves. It's also sending out radio waves. It's sending out X-rays, gamma rays. It's sending out all of them. What if you get a bigger star? What if you get one of those really big blue giant stars? What's going on there? Well, for a blue giant star, it's going to have that same shape, but it's going to peak in the blue. It's also emitting a fair amount of ultraviolet and green and yellow and orange and red, but it's going to dominate with that blue. Not to mention all the ultraviolet it's emitting and all the infrared, etc. that it emits. So, in that way, we can see what's going on with these random collisions and what colors they emit. This is also what happens when you're measuring your temperature. With that little thermometer that you point at your forehead and you click a button and it just tells you. What it's doing is it's reading the output from your the output of different colors coming from your head. Now, in the continuous spectrum that we're looking at, it's going to peak in the infrared, and it's going to be corresponding with a very specific maximum in the infrared, and that's going to tell them, oh, since it peaked at that specific temperature, at that specific wavelength of light, then the temperature must be 96.8, or maybe it's not. Maybe it's at 90. That's a bad thing. Maybe it's at 100. Not a very good thing. Maybe it's at 106. Then you're dead. Okay, I don't think you can survive 106. At least not for very long without your brain melting. a synapse is just not firing right and stuff. Okay, this is called black body radiation. Okay, this stuff that's just infrared, we can't see that. Fire, we see it as mostly being orangish red. For the sun, do not look at the sun. But for the sun, it peaks in green, but it doesn't look green. It actually looks whitish. That's because so much of all those colors comes through that our eye, it just saturates all of our detectors and it looks white. Or it destroys our eyes, one of the two. Blue giants, so much more blue and purple is there that it looks bluish purple. So, big considerations to have for the color that it seems to be. Okay. That's our continuous spectrum of polychromatic light. So, quick summary there. Skipping a few things. What types of light? Monochromatic light. Most lasers are monochromatic. We can have discrete polychromatic sources like atomic sources and molecular sources. Or continuous polychromatic. So randomly moving and vibrating stuff. I'm going to not say molecular. And black body radiation, discussed. Okay. That's our considerations there. What types of light? I used to give a quiz at this point on Lloyd's mirror, but I've skipped it. Doing all these warm-ups instead of quizzes. The last thing on these notes here is the stuff I covered the other day about polarizers. Okay. And there's some fun stuff with polarizers as well that I didn't really get into. You could talk more about the 3D effect, and you could talk about how they're used in on screens and all sorts of stuff like that. Or you could also look up on the Oatmeal, which is the Oatmeal is a comic page, a webcomic, and look up the rainbow shrimp I'm missing a word. I'm missing a word in the middle. Mantis. The rainbow mantis shrimp. It is interesting. Okay? And the Oatmeal has a really cool article on them. So, really fun stuff. They take a few liberties. They use the term velocity in a way that I was not happy with. But they've got some interesting information about, in a very open-ended way, of how there are mantis shrimp that can actually see different polarizations. They don't specify that, but that's what they're basically saying. One downside of this, because it's a webcomic, it glosses over some important and interesting details, but there's other places to research. This is just the most fun source for it. Where does that leave us? That leaves us with one more topic to cover. The dog always likes to snore in the middle of my videos. Hope you guys are going to be okay with not having Jack in the videos anymore. This will be your last video with Jack in it, because he's not. I didn't have him last summer, so he's not in the video from then. Okay, so keep snoring, Jack. And he's suddenly quiet. Last topic. The the photoelectric effect. The photoelectric effect is about light because it's about photons, and it's about electrons because it's electric. Okay. And more so than that, it's about a way, not every way, but a way that they can interact. Specifically when we're dealing with electrons in a conductor, or rather on a conductor. Okay. So that should be a flashback to 15 weeks ago when we first started talking about electrons moving around conductors. But this time we're going to be looking at the atomic scale to look at what's going on with these electrons and how light can interact with them while they're still interacting with the conductor. The photoelectric effect was first published in 1905, which was a very special year. It's the year that Albert Einstein posted this, and it's also the year that he published his paper on E equals mc squared. That's ridiculous, because this one is a topic worthy of a Nobel Prize. This one is a topic worthy of a Nobel Prize, and not many people in a career did work that was worthy of basically 2 Nobel Prizes. I'm not saying that he won 2. I'm just saying that they were both worthy of it. And no one's done that in 1 year. No one's released papers that were worthy of a Nobel Prize both in the same year. More so than that, it's not just one topic and then just slightly different topic like most people do, where they're just getting a little bit better in the field and a little bit better in the field and a little bit better. These are completely different topics. Okay, so completely different topics in the same year, and that's about all I'm going to gush about Einstein. Instead, let's get to the physics. Conductor. These electrons are bound to the conductor. Okay. In fact, the electrons are able to jump from one atom to the other in the conductor. They do this at a very special energy level. Okay. So I'll start with my distinction between free and bound again. And then down here, we have what's called the conduction band. Another name that you might see for it is the Fermi energy level. I like calling it the conduction band because it ties back to the fact that we're dealing with a conductor. A common material that's used for this experiment is zinc as your conductor. For one, it's really, really cheap. It's so cheap that that's what we stuff our pennies with. Pennies are copper on the outside and zinc on the inside, which is very fun to boil. It's also useful because this jump, the amount of work required in order to free the electrons that are down here is an amount that is totally reasonable. It's an amount very close to the purple in the visible spectrum. So, important consideration. But it also tells us that red is not enough energy. So what happens when red light comes in? and hits one of these electrons. Well, it gives it a specific amount of energy, and that would be however much energy was in that singular photon. So it boosts the electron up, but the electron comes right back down. It's much like the idea of what goes up must come down. Which is true if you're throwing stuff, because if we're standing on Earth and we throw a ball, we're not going to throw it into orbit. We just don't have that much strength in our arms. We need a rocket in order to do that. So let's give this thing the jet fuel that it needs. Let's have some purple light come in. The purple light comes in, and it's got more energy. It's got enough energy to actually kick that electron out. So it spends all of that work function, and then it's got a little bit left over too. It's got some leftover energy that it can use as kinetic energy. Okay, so we got some energy in, and we got some energy out. The energy in came from the light, and the energy of a single photon is Planck's constant multiplied by the frequency of the light. The energy out, some of it went back to the atom, the work function of the atom, plus the kinetic energy of the electron. So, and those add up. I want to be able to measure this leftover energy. How can I measure this leftover energy? Well, it's an electron. I can collect an electron. So we do this experiment inside of a capacitor. Okay. And we attach that capacitor to a voltmeter and some other electronics as well. But really what I care about is the voltmeter and the capacitor. You're setting in your purple light. It's causing electrons to jump off of that surface and go to here, which is charging up the capacitor. It's making that side more negative. That side becomes more negative. Well, that means you got lonely protons over here. That's setting up a potential difference. How can I measure the kinetic energy with this thing? Well, as this thing charges more and more and more, it takes more and more energy for the electron to get to the negatively charged plate. So there's going to be a max voltage difference that occurs, where once there's this voltage difference across there, the electron cannot get across anymore. And it was all because we have a capacitor that is charging for some time, all the way to some Vmax. When it reaches or approaches that Vmax value, that Vmax, if I multiply it by the charge of an electron, is the potential energy that the electron's trying to traverse. In other words, HF is equal to the work function plus the charge of an electron multiplied by Vmax. This is usually rewritten to be EV max is equal to the h Planck's constant multiplied by the frequency of the light minus the work function. This equation is usually graphed as well. And you do this for many different frequencies of light. And for your higher energy lights, you do get some data points. But you don't get these data points. You do get that the slope is equal to Planck's constant. For the value of Planck's constant, you can check the front of the book. It's right there. It's a universal constant. It's the same everywhere in the universe. But at the low energy, remember that the red light did not cause emission. No emission means no free electrons. No free electrons means you never charge up the plate. And if you never charge up the plate, the voltage is going to stay 0. There we go. That's the data you get for this experiment. Something weird about it is it has no intensity dependence. You can send in a whole bunch of light, but that has nothing to do with how much light. This has nothing to do with how much light. This has nothing to do with how much light. We've got the work function completely depends on what material you're using. How big is that jump from the Fermi energy conduction band all the way up to being free? That's all the W is. H, universal constant, Planck's constant. E, charge in an electron, universal. Vmax, well, that's your measuring. Frequency, that's the frequency of the light you're using. Okay, so at no point in here is the brightness of the light important. What that means is that every time the photon comes in, it's a one photon, as in one little bit of light, one electron interaction. In that way, the light is coming in, it's hitting the electron, and it's transferring all of its momentum and also all of its energy to the electron. Momentum and energy. In that way, it's giving everything it can in the way that particles interact. Okay, so it's just one example of light acting like a particle. All right. So what did we do today? We have photoelectric effect. We looked at an atomic process that connects ideas of electrons from way back early in the semester to ideas of light from this late part in the semester. We talked about collisions, an idea from 2A. But we talked about them and temperature, another idea from 2A, in terms of how can we observe the temperature of things? How can we see just how hot they are? Well, if they're a black body radiator, we can look at the distribution of colors that come off of it, or wavelengths, as is more appropriate for non-visible light, or wavelengths. And we use that information to say, oh, if it peaks at this frequency or wavelength, it must be at this temperature. If it peaks at this much smaller wavelength, well, it must be hotter. It must be hotter And if it's in the infrared, it must be colder. And we went over the hydrogen spectrum and how that hydrogen spectrum tells us about the atomic nature of atoms, how they're very specific energy levels that electrons can habitate in, and for that reason, there are only very specific colors or wavelengths of light that the different atoms or different molecules can emit. Many times it's not as simple as this, though. Like it's a small number of transitions. When I was doing my research for my master's, I was looking at para water and ortho water. What makes them different is the magnetic properties of the two hydrogens, whether they have a spin that is parallel or orthogonal. For each of these, I was simulating 200. Actually, I forget if this is 109 or 209. It's probably only 109 levels here, 109 levels there. And I wrote a program that actually analyzed the different transitions that could happen for all of these energy levels and all of these energy levels. And based off of that, how bright the light would be that comes off of that ortho water, off of that para water, and also I threw in molecular oxygen with it. Okay. Most of these are in the infrared spectrum, and that's the region I was trying to consider. Now, this is not the best data. It turns out that once they did the observation, they said, nope, that's not quite right. So my thesis advisor actually went on and published more papers on the topic. But this idea of energy levels is still open for a lot of research, considering more and more complicated systems of atomic structure. Okay. That is optics for you. Okay, that's light. That's some atomic structures and how that's connected to light as well. Don't forget to do your discussion. Feel free to watch this as soon as you can as well. Do try to get this discussion done before Tuesday night. And if you don't send me an email or talk to me in some other way before then, good luck on the final. And I will try to get grades out as soon as I can after the final. Okay. Thanks for a fun semester, and and good luck.